What if I told you that your electrical system could be wasting up to 20% of its capacity right now without you even knowing it? Well, today we're diving deep into something called power factor correction. It's a concept that helps your system work smarter, not harder, and it can save you from some serious costs. Let's get into it. Yeah, you heard that right. A low power factor forces your entire system to draw way more current than it actually needs to get the job done. And that means wasted energy, it means you need bigger, more expensive equipment, and you can even get hit with some pretty hefty financial penalties from your utility provider. So, understanding this and fixing it is absolutely key to running an efficient system. Okay, so before we can fix the problem, we've got to understand it, right? Let's break down what's really happening inside an electrical system when that power factor starts to drop. This slide is perfect. The best way to think about this is like a glass of beer. Seriously, the beer itself, that's the active power. It's the useful stuff, the part you actually want. The foam on top, that's reactive power. It takes up space in the glass, but it doesn't do any useful work. And the entire glass, the beer plus all that foam, that's the apparent power. That's what the utility company has to generate and send to you. So our goal is super simple. Minimize the foam. So where does all this foam, this reactive power, actually come from? Well, it's generated by any equipment that has magnetic windings. Think big motors, transformers, stuff like that. We call these inductive loads, and they're the culprits that cause the current to fall out of sync with the voltage, which is what makes the whole system so inefficient. And this right here shows you the real-world consequences. With a low power factor, your system is drawing a ton more current just to do the same amount of work. This leads to more energy loss, you need beefier, more expensive cables and switchgear, and yep, there are those penalty charges we talked about. It's just a bad scene all around. Okay, so we've laid out the problem, but the good news is there's a really elegant and effective solution. It's time to bring in the hero of our story, the capacitor. So here's how it works, broken down really simply. Our motors, those inductive loads, they create a lagging reactive current. Now capacitors do the exact opposite. They provide what's called a leading reactive current. So when you add capacitors to the system, their leading current essentially cancels out the lagging current from the motors. The end result? A much, much healthier power factor, getting you way closer to that ideal target of 1.0. Now, are there other ways to do this? Sure. For massive industrial operations, you might see things like synchronous condensers. But look, for almost every commercial building or factory out there, static capacitors are, by a long shot, the most practical and cost-effective choice. So, we know we need capacitors, but that brings up two absolutely critical design questions. Where exactly do we put them, and how much corrective power do we actually need? Let's get into the nitty-gritty of system design. As a designer, you've basically got three main strategies. You could do local correction, putting a capacitor right at each individual motor. That's super effective for reducing current all through your wiring, but that can get pretty expensive. Or you could do distributed correction at a subpanel. But honestly, the most common approach by far is bulk correction, installing one large capacitor bank right at the main intake. This fixes the power factor for the whole site, which is what the utility company really cares about. This is the key question, right? It's the one every design engineer has to answer. You can't undercorrect because you'll still face those penalties, but you definitely can't overcorrect either. So how do you find that perfect sweet spot? Well, you can figure it out with a simple calculation table just like this one. And trust me, it's way easier than it looks. Just find your current power factor in that first column. Let's say it's a pretty bad 0.75. Then find your target along the top. We're aiming for a healthy 0.95. The number where they meet, 0.55, that's your magic multiplier. You just multiply your total power in kilowatts by that factor and boom, you've got the exact size of the capacitor bank you need in kVAR. Simple as that. But here's the thing, a factory's load isn't constant, right? It changes all day as shifts start and end and machines turn on and off. That's why you can't just install one giant capacitor and call it a day. That's where automatic controllers come in. Think of them like a smart thermostat for your power factor. They're constantly monitoring the system and switching smaller capacitor banks in and out step by step to perfectly match the real-time needs of the system. This also prevents a really dangerous overcorrection. Okay, let's put all this theory into practice. We're going to look at a real-world scenario, and then we'll cover some critical precautions you absolutely have to consider when you're designing one of these systems. Check out the impact here. It's pretty amazing.
We have a factory that was running at a pretty poor power factor of 0.78, and they were getting hammered with penalties every single month. After they installed a correctly sized automatic capacitor bank, they boosted their power factor all the way up to a solid 0.96. And the results? They speak for themselves. Lower current draw, no more penalties, and a lot less stress on their expensive transformer. That is a tangible, real-world win.
Now, before you run out and install a system, there are 3 critical warnings you need to hear. First, standby generators can become really unstable with high power factors, so your PFC system has to be automatically disconnected whenever the generator kicks in. Second, modern electronics create a kind of electrical noise called harmonics. These can dangerously resonate with your capacitors, kind of like a specific sound frequency shattering a wine glass, so you might need special filters. And finally, never, ever overcorrect. Pushing your power factor too high can cause major problems for the utility grid itself.
So there you have it. Power factor correction isn't just some abstract theory. It's a powerful, practical tool for building smarter, more efficient electrical systems and making every single kilowatt count. And now that you can spot this hidden inefficiency, it kind of makes you wonder, what else is lurking in our electrical world that isn't quite as straightforward as it seems? Let us know what you want us to explain next.